Today, we are pulling back the curtain on one of the greatest marvels of modern aviation. We're going to explore that incredible network of systems that lets a massive aircraft navigate the entire globe with, well, pinpoint accuracy. I mean, have you ever really thought about it? How does a machine, a 400-ton machine, hurtling through the sky at 500 miles an hour, often in total darkness or thick cloud, how does it have such a perfect sense of itself and the world around it? Well, I can tell you it's not magic. It's actually an invisible symphony of instruments, and we're about to break down exactly how it all works. So let's dive right in. The best way to think about this is to imagine an aircraft having senses, just like we do. And the most fundamental of all of them is its sense of touch. You know, how it literally feels the air rushing past it. This right here is the bedrock of all flight instrumentation. And it all starts on the ground with a simple physical check. Seriously, before every single flight, pilots walk around and inspect this series of small tubes and holes on the outside of the aircraft. These are the openings for what's called the pitot-static system. They have to make sure they're clear of any obstructions. We're talking bugs, ice, you name it. And they confirm that the internal heaters are working. And that last part is absolutely critical to prevent ice from blocking them up in flight. Now, what's so cool about this is just how elegantly simple the principle is. The system measures two things. First, you've got pitot pressure, which is the total pressure of air ramming into a forward-facing tube. Then you have static pressure, which is just the still ambient air pressure measured from little vents on the side of the plane. The aircraft's computer just subtracts one from the other, and voila! The result is dynamic pressure, a direct measurement of the force of the moving air. And that is how we get our airspeed. And this slide just illustrates how incredibly efficient the whole setup is. Those two simple pressure readings feed four critical instruments. Your altimeter and vertical speed indicator, they only need that static pressure to tell you your altitude and if you're climbing or descending. But the airspeed indicator and the Mach meter, they need both pitot and static pressure to figure out how fast the plane is ripping through the air. It is literally the foundation of awareness in the cockpit. Okay, so now the plane can feel its speed. That's a great start, but what about its orientation? How in the world does it know which way is north, and maybe even more importantly, which way is up? For that, we're going to need a sense of balance and direction. Now, you might be thinking, just use a compass, right? But here's the thing. In an aircraft, a simple magnetic compass is surprisingly unreliable. During turns or when you accelerate, inertia just throws the compass all over the place. And if you get near the poles, it actually tries to dip towards the Earth. So what's the solution? The gyroscope. It's basically a perfectly balanced, rapidly spinning wheel that, because of something called rigidity in space, hates any change in its orientation. It doesn't care if the plane turns or speeds up, it just stays pointed in the exact same direction. So, here's the crucial takeaway. This amazing gyroscopic stability does two absolutely vital jobs. You mount one gyro horizontally, and it becomes your directional gyro, giving the pilot a rock-solid heading. Then, you mount another one vertically, and it creates an artificial horizon, showing the plane's attitude relative to the real horizon. So even in zero visibility, the pilot knows exactly which way they're pointing, and, thank goodness, which way is up. So far, we've talked about the fundamental mechanical principles that pretty much governed aviation for decades. But then everything changed. The digital revolution arrived. You have to picture it. For most of aviation history, cockpits were this crazy blizzard of individual analog dials. Every single instrument, airspeed, altitude, heading, engine temp, it was its own separate mechanical device. A pilot's job was this constant scan of dozens and dozens of these steam gauges. That is, until powerful microprocessors came along and allowed the entire cockpit to be completely and utterly reinvented. So instead of raw data going to all these individual gauges, everything now flows into central computers. The Air Data Computer, or ADC, takes this pitot and static pressures, corrects for any little errors, and sends out perfect digital data. The flight management system, the FMS, that's the brain holding the entire flight plan. And the Electronic Flight Instrument System, or EFIS, displays all this information on what we now call a glass cockpit. Just a few clear, simple screens. The result? A massive leap forward in safety and efficiency. It changed everything. Okay, so it's at this point now that all these individual systems are talking to each other that they can finally come together to perform the ultimate act of coordination, fully automated flight.
See, the autopilot isn't really a single instrument. It's more of an integration system. Think of it as the conductor of the orchestra. It's listening to the air data computer for speed and altitude, it's listening to the gyros in the FMS for its heading and flight path, and it synthesizes all of that information to make tiny, constant adjustments to the flight controls. It flies the plane with the precision that's almost impossible for a human to replicate by hand.
And the absolute pinnacle of this automation is something called the autoland. Imagine near zero visibility. The system locks onto radio beams from the runway. We call this the Instrument Landing System, or ILS. Then, below 1,500 feet, a second, redundant autopilot kicks in just for safety. At just 50 feet above the ground, it enters flare mode, gently raising the nose. The throttles automatically pull back to idle, and the plane touches down, perfectly on the center line, all without the pilot's hands on the controls. It's incredible. But wait, how does it know it's exactly 50 feet off the ground? The standard pressure altimeter just isn't accurate enough for that kind of precision. Well, the secret is the radio altimeter. At about 2,500 feet above the ground, this system wakes up and starts bouncing radio waves off the surface to get a hyper-accurate, real-time reading of the plane's height above the terrain. And that is the essential piece for that final, critical phase of landing. All right, so finally, behind all the systems that tell the plane how to fly, there's this whole other layer working constantly in the background, a safety net, if you will, of unseen guardians in the cockpit. These are the systems that are always watching your back. You've got the Traffic Collision Avoidance System, or TCAS, which is constantly scanning for other aircraft, and it'll give pilots alerts and even tell them to climb or descend to avoid a collision. Then there's the Ground Proximity Warning System, or GPWs, which monitors the radio altimeter and flight path, screaming at the pilots if they get dangerously close to terrain. And of course, the famous black boxes, the flight data and cockpit voice recorders, which silently record every parameter and conversation just to make sure that if anything ever does go wrong, the entire industry can learn from it. So, from simple air pressure to a fully automated landing, this whole symphony of technology has made flying extraordinarily safe and reliable. Which kind of leaves us with one last question to ponder. With planes that can now practically fly themselves, what is the most important system left in the cockpit? Well, maybe, just maybe, it's the one system that's been there from the very beginning. The well-trained, professional human crew that's managing it all.